If you take a $5,000 like professional cinema camera, right, and you mount it securely to a superbike moving at 100 miles an hour.
Oh, yeah, and just hit record.
Exactly. You
Yeah.
hit record, and you might expect to get this cinematic masterpiece. But you know what you actually get?
Completely unusable garbage.
Literally a shaky, vibrating, wind-blasted mess. I mean, the rolling shutter alone will make the world look like it's made of jelly.
Yeah, and the audio will just be this concussive wall of static.
Right. And yet, you can take a $400 piece of plastic, strap it to your helmet, and suddenly you produce this Hollywood-grade visual experience that makes you, the viewer, actually feel the G-forces in your chest.
It is a massive technological paradox, isn't it?
It really is. And today we are decoding the bizarre physics and engineering of why that happens.
Because the environment of a motorcycle traveling at speed is actively hostile to optics.
Right.
And to audio, and definitely to delicate electronics. I mean, it is an environment of intense high-frequency vibration, massive aerodynamic drag.
Not to mention extreme swings in lighting and temperature.
Exactly. So bridging the gap between the raw, chaotic reality of riding and creating a smooth, cinema-grade visual experience, well, it requires essentially hacking both the hardware and the software to replicate human perception.
Or sometimes exaggerate it.
Right, exaggerate human perception.
And that is exactly our mission for this deep dive. We are going to break down the ultimate technical configurations required for professional motovlogging.
We're talking about optical physics, acoustic engineering, biomechanical safety.
All of it. And to make sure we aren't just discussing this in a vacuum, we're applying all of these theories to one of the most extreme, borderline, terrifying machines on the market today.
The 2025 Ducati Street Fighter V4S.
It is going to be our ultimate test subject. I mean, if a camera setup can survive this bike, it can survive anything.
Yeah, absolutely.
And we got a massive stack of data in front of us. We are pulling from advanced academic research on POV motorcycle cinematography, the latest biomechanical safety studies regarding helmet impacts,
Rotational force, yeah.
highly technical audio routing schematics, detailed ECU tuning data from the engineers at BT Moto, and an exhaustive track-based hypersport tire test.
It's a lot to cover.
Okay, let's unpack this.
Yeah.
Because before we can even look at the Ducati, we have to look at the glass. You know, the physical hardware that is actually capturing the light.
That's the perfect starting point, because a modern action camera is, it's no longer just a toy you stick on a dashboard with double-sided tape.
Right.
It is a highly complex computational optical platform. And when you dive into the data on professional motovlogging setup, you quickly realize that the hardware developers have kind of split the industry into two very distinct architectural paths.
Okay, so two paths.
Yeah. You have to choose your hardware based on the specific physics of what you were asking the sensor to do. The first path is the premium large sensor cinematic tool,
Okay.
which is perfectly exemplified by the GoPro Mission 1 Pro.
Right, the Mission 1 Pro. Now, the spec sheet on this thing boasts a 1-inch CMOS sensor, which, you know, for someone who usually just shoots on their phone, a 1-inch sensor might not sound massive.
Sure.
But in the action camera world, that is a monstrous piece of silicon, right?
It really is. And to understand why that matters, you sort of have to think about a camera sensor as a physical net designed to catch photons of light.
Okay, a net for light.
Right. A standard action camera has a very small net. But the Mission 1 Pro's 1-inch sensor has drastically more surface area. It's this 50 megapixel beast that can process 8K video at 60 frames per second.
Wow.
Or, you know, it can drop down to 4K and shoot an incredible 240 frames per second for ultra slow motion.
That's insane. But the resolution isn't actually the secret weapon here, is it?
No, not at all. The real engineering magic lies in the pixel architecture itself. Specifically, this process called quad Bayer pixel binning, which the camera utilizes heavily when you configure it for 4K capture.
Let's pause on that, because pixel binning sounds like a buzzword for, I don't know, digital recycling. What is physically happening on the surface of that sensor when it bins pixels?
Essentially, the processor is taking 4 adjacent physical pixels on the sensor, and each of those is measuring about 1.6 micrometers, and it's electrically fusing them together into a single, massive 3.2 micrometer fused pixel.
So the camera is intentionally sacrificing its total maximum resolution to create bigger individual buckets to catch the light.
Precisely. Let's use a physical analogy. Imagine photons of light as raindrops, right?
Okay.
And the pixels on the sensor are literal buckets sitting out in a field. A 50 megapixel sensor has 50 million tiny buckets. In low light, those tiny buckets struggle to collect enough rain.
Makes sense.
But in extremely bright light, like direct midday sunlight, those tiny buckets fill up instantly and just overflow.
And in the digital camera, that overflow is what causes a blown-out image, right?
Exactly.
Yeah.
Where the sky just turns into a blinding, featureless white block and all the cloud detail is permanently destroyed.
Yeah, you see that all the time.
But by electrically combining 4 small buckets into one giant bucket, the sensor can suddenly handle a massive deluge of light without overflowing.
Wow.
And for a motorcycle rider, this specifically solves the most frustrating historical problem of action sports.
Which is the high contrast transition. Oh, man.
Yeah.
Every rider knows this exact scenario. You're riding down a canyon road, twisting through a heavily shaded forest canopy.
Yeah.
The camera exposes for the dark shadows, and the trees look incredibly detailed and moody. But then you round a corner and suddenly break out into an open, sun-drenched highway.
And what happens?
For 5 agonizing seconds, your video just turns into a blinding white screen while the tiny internal processor panics and tries to adjust. It completely ruins the shot.
Exactly. But with quad Bayer pixel binning, the Mission 1 Pro's sensor is capturing light with those massive fused pixels, and that allows it to retain up to 14 stops of dynamic range.
Which is huge.
It's massive. Dynamic range is simply the measurement between the darkest shadow the camera can see and the brightest highlight it can see simultaneously.
So with 14 stops.
With 14 stops, the camera can stare directly into the dark, shaded mechanical crevices of the motorcycle's engine block, while simultaneously resolving the bright, fluffy textures of the clouds in the sky without losing data in either extreme.
It's incredible technology. But that brings up an obvious question for me. If the Mission 1 Pro and its massive 1-inch sensor are so capable, why is there a second hardware path? Why would any professional motovlogger use anything else?
Because physics always demands a trade-off. That massive sensor requires a larger glass lens to focus the light, and it requires an incredibly powerful heat-generating processor to crunch all that data.
So it's heavy and gets hot.
Right. That means penalties in physical weight, aerodynamic drag, and thermal management. So Path 2 is the highly modular aerodynamic action camera.
Okay, like what?
Which is typified by the GoPro Hero 13 Black. It uses a much smaller 11.9-inch sensor, but it solves the motovlogging puzzle, not with sheer size, but with geometry. It utilizes an 8.7 native aspect ratio.
An 8.7 aspect ratio. So instead of a rectangle, the sensor is almost a perfect square.
Yes. And the geometry of that square sensor completely changes the framing workflow. It solves a massive headache for riders.
How so?
Well, think about the historical action camera. They all shot in a 16.9 aspect ratio, which is a wide horizontal rectangle, just like a television screen.
Right.
If you mounted that wide rectangle to your chin bar and then you leaned forward into an aggressive tuck on a sport bike, what would happen?
Oh, the camera would end up pointing straight down at the asphalt, completely cutting off the horizon. The viewer would just be watching pavement blur by.
Exactly. Alternatively, if you angled the camera up to catch the horizon before you got on the bike, the moment you sat up straight at a stoplight,
You'd just be filming the sky.
yeah, and you'd lose the motorcycle's dashboard entirely.
And if you are watching a video of a superbike, seeing the dash is half the fun. I mean, you want to see that massive 6.9-inch TFT display on the Ducati. You want to see the speed, the RPMs climbing to redline, the lean angle data, the gear indicator. You want context.
Exactly. Context is what makes it a vehicle review and not just a floating magic carpet ride. The 8.7 sensor captures maximum vertical data. It records a tall, nearly square field of view.
Oh, that makes so much sense.
This means you don't have to guess the perfect mounting angle in your garage before you ride. You just point it forward. Later, in post-production, that massive square image gives you the mathematical leeway to literally slide a 16.9 widescreen crop box up or down across the captured footage.
So you can frame it perfectly after the fact.
You can dial in the framing perfectly to capture both the motorcycle's instrument cluster and the horizon simultaneously.
That's brilliant.
And even better, it allows for lossless reframing to a 9.16 vertical format for social media shorts. You shoot the ride once, and from that single square file, you can punch out a horizontal cinematic video for YouTube and a vertical short for TikTok.
With zero loss in underlying resolution.
Zero loss.
The efficiency of that workflow is undeniable. Now, the material does mention some alternative setups beyond these two main action cameras. For instance, using a Sony ZV-E10 II, which is a heavy APS-C mirrorless camera mounted directly to a tank bag.
Yeah, that's an option.
And that gives you that gorgeous cinematic shallow depth of field where the dashboard is in sharp focus, but the road ahead is softly blurred. And there's also the 360-degree camera option, the GoPro MX2, mounted to the rear subframe on a carbon fiber pole.
Right, the invisible drone look.
Yeah, that gives you those crazy perspectives where you're watching yourself ride from behind and you don't even have to aim the lens while you're moving.
Those are incredibly powerful tools, but we have to classify them properly. A mirrorless camera on a tank bag or a 360 camera on a pole are B-roll cameras. They are fantastic for establishing shots or secondary angles. I mean, the 360-degree camera captures a full 8K sphere of data, so you can digitally pan around the motorcycle in post-production.
But not for the main view.
No, however, for the primary point of view, the visceral first-person perspective that carries the narrative of the ride the dedicated action camera remains king, simply due to its aerodynamic profile, its vibration resistance, and its safety.
Which brings up something I hear constantly from new riders. They always ask, why not just strap my brand new smartphone to my chin bar?
Oh boy.
They're like, the cameras on these phones have multiple lenses, they shoot 4K, they're amazing. And I always compare using a dedicated action camera over a smartphone to the difference between wearing a tailored leather race suit versus wearing a plastic raincoat.
That is a very apt comparison.
Right. Sure, they both technically cover your body and keep the wind off you. But one is aerodynamically sculpted, armored with Kevlar, and engineered specifically to survive the violent, abrasive extremes of the environment. And the other will literally flap to pieces and disintegrate at 100 miles an hour.
Yeah, your smartphone's optical image stabilization relies on tiny, delicate, floating magnets.
Yep.
The high-frequency buzz of a motorcycle engine will physically shatter those magnets within an hour, ruining a $1,000 phone.
That is a highly accurate and expensive reality check.
Furthermore, a smartphone lacks the specialized digital lenses found in action cameras. The digital lens you select in the software, whether it's linear, superview, or hyperview, drastically manipulates the viewer's perception of speed.
I've always had an issue with superview, though. I'll admit it. It feels like a cheat code for motovloggers.
How?
Well, you are telling the software to stretch the edges of the frame to artificially warp the peripheral vision. It makes the ride look incredibly fast, but it also severely distorts the geometry of the motorcycle's handlebars. They look stretched out and bent. Doesn't that ruin the technical accuracy of the video? Shouldn't we just stick to a linear lens?
That is a completely valid critique of the geometry, but what's fascinating here is that it misses the psychological goal of the cinematography.
Okay, explain that.
If you use a linear lens, the software digitally removes the barrel distortion, keeping all the lines perfectly straight. It is visually accurate and very natural.
Sounds good so far.
It's fantastic if you are filming a slow, technical breakdown of the motorcycle suspension in a garage. But speed on a screen does not feel like speed in real life.
Oh, that's true.
When you are physically on the bike moving at 80 miles per hour, your adrenaline is spiking, the wind is roaring, and your brain naturally focuses entirely on the vanishing point ahead, causing your peripheral vision to blur. It feels intensely fast.
But on video?
If you film that exact 80-mile-per-hour ride with a straight, narrow linear lens and watch it later on a small screen, it looks like you are casually cruising through a neighborhood at 30 miles per hour. It looks boring.
It flattens the experience.
Exactly. When you switch to a superview or hyperview digital lens, the camera captures a massive field of view and then dynamically stretches the peripheral edges to fit a standard screen. It compresses the outside edges.
So it forces that tunnel vision.
Yes. When you ride forward, objects on the side of the road, trees, guardrails, lane markers, they enter that compressed edge and appear to warp past the lens at an accelerated rate. It creates an immersive tunnel vision effect.
Okay.
Yes, it warps the handlebar slightly, but it translates the feeling of velocity into a two-dimensional medium. It makes the viewer feel the speed that the rider is actually experiencing.
Okay, I can accept that. We are trading slight geometric distortion for emotional accuracy. So we've selected our hardware, we understand the sensor architectures, and we have our digital lenses set. But here is the harsh reality the research points out. If you take all this incredible technology, mount it to your helmet, and just leave the camera on auto while you ride at high speeds, you are asking for trouble.
Oh, absolutely.
To get true cinematic footage, we have to manually engineer the exposure. We have to essentially hack the camera's shutter to replicate human vision.
And that entire hacking process begins with understanding shutter mechanics, specifically the 180-degree shutter rule.
Okay.
If there is one foundational rule of motion picture cinematography that separates amateur footage from professional film, this is it.
We absolutely have to break this down because ignoring this rule is the single biggest reason why most amateur motorcycle footage looks like a cheap, jittery soap opera instead of a movie.
The 180-degree rule dictates that your shutter speed must be the mathematical reciprocal of twice your frame rate.
Okay, so give me an example.
So, let's say you want your motorcycle footage to have that classic cinematic movie-like cadence. You generally set your camera to record at 24 frames per second, which is the standard for Hollywood films. Following the math of the rule, 2 times 24 is 48.
Right.
Therefore, you must dive into the camera settings and lock your shutter speed at exactly 148th of a second. If you are shooting a high-speed track day and want smooth 60 frames per second video, your shutter speed must be locked at exactly 120th of a second.
Okay, the math is simple enough, but what happens mechanically if you ignore that? Let's say I leave the camera on auto, which is what 99% of people do. What is the camera doing wrong?
Well, if you leave the camera on auto and you ride your motorcycle out of a dark garage and into bright midday sunlight, the camera's processor is going to try to protect the image from overexposing.
Okay.
It sees all that light and panics. Since action cameras have fixed apertures, the hole letting light in can't get smaller. The only tool the camera has to reduce light is to speed up the shutter.
Right, because the whole size is fixed.
Exactly. So it might crank the shutter speed up to 11,000th or even 12,000th of a second. At that incredibly fast speed, every single frame of the video you capture is perfectly, crisply frozen in time. There is absolutely zero blur.
Which, if you're a photographer, sounds amazing. You want a crisp image.
It is amazing for a still photograph, but it is visually catastrophic for a video in motion.
Yeah.
Human eyes do not perceive the world in perfectly frozen, crystalline frames.
Right, we see motion blur.
Yes. If you wave your hand in front of your face right now, you don't see a sequence of perfectly sharp hands, you see a blur. When a camera records at a super fast shutter speed and you string together 24 perfectly frozen, ultra-sharp frames every second, the resulting video looks incredibly harsh, staccato, and jittery.
Oh yeah, where the background seems to strobe or skip as you turn.
Exactly. You completely lose the smooth, flowing sensation of speed. By locking the shutter speed at 148th of a second, you are forcing the camera to keep the shutter open just a fraction of a second longer.
Just long enough to catch that blur.
It stays open just long enough for the asphalt and the passing trees to physically drag and blur slightly across the sensor in each frame. When you play those frames back, that inherent motion blur links the frames together visually, creating natural, fluid motion that mimics how the human brain processes speed.
But there's a massive catch here.
Yep.
If you lock your camera's shutter speed at a relatively slow 148th of a second on a bright, sunny Tuesday afternoon, you're letting way too much light hit the sensor. The camera can't speed up the shutter to protect itself anymore.
Right.
The result is going to be completely blown out. You'll just record a glowing white rectangle.
Exactly. You have intentionally removed the camera's ability to control its own exposure via the shutter. The digital software can no longer help you. So you have to introduce a physical mechanical barrier. You must use neutral density, or ND, filters.
ND filter.
You literally take a piece of specialized darkened optical glass and screw it directly over the front of the camera lens. It acts exactly like high-end sunglasses for the camera sensor.
It's all about reducing the volume of photons.
Precisely. If you are riding in bright, direct, cloudless sunlight, you would thread on a very strong filter, like an ND32 or even an ND64, which blocks a massive percentage of the light from ever reaching the sensor.
Okay, and if it's cloudy?
If you're riding on a day with intermittent clouds, you might drop down to an ND16 or an ND8. The crucial part of an ND filter is the word neutral. It reduces the overall intensity of the light hitting the sensor without altering the color balance.
So it's just pure darkening, no color shift.
Exactly. By putting sunglasses on the camera, you restrict the light physically, which allows you to maintain that slow, cinematic 148th shutter speed without blowing out the sky.
Okay, so we've got the motion blur dialed in with ND filters. But our documentation harps heavily on data compression, specifically 10-bit color depth and GP-Log2 profiles.
Yes.
Now, earlier we talked about the 1-inch sensor keeping the sky from blowing out. But shooting in a log profile takes that to another level. We need to talk about logarithmic compression.
This is where modern action cameras have truly blurred the line with Hollywood cinema cameras. Think about the standard video profile on your smartphone. It applies a very aggressive, high-contrast mathematical curve to the video before it saves it to the memory card.
Okay.
It intentionally crushes the dark shadows to make them deep, pitch black, and it pushes the bright highlights to make them stark white. It does this because it wants the video to look punchy and saturated the second you open it on Instagram.
Right.
The problem is, when the camera crushes those shadows and pushes those highlights, it permanently deletes the data in those extremes to save file space.
Right. It bakes the contrast in and throws away everything else.
Yeah.
Which means if you try to brighten up the shadow of the motorcycle engine later to see a mechanical detail, there's nothing there. It just turns into gray, noisy sludge.
Exactly. But if you dive into the ProTune settings and enable GPlog through on the Mission 1 Pro or GPlog on the Hero 13, you are telling the camera's computer to stop throwing data away. The camera applies a mathematical logarithmic curve to the image. It redistributes the tonal data across a very flat, low contrast spectrum. It intentionally pulls the bright highlights way down, and it aggressively lifts the dark shadows up.
But it looks terrible when you first view it, right?
When you look at log footage on the camera's back screen, it looks terrible. It looks incredibly dull, gray, desaturated, and muddy. But it isn't muddy. It is incredibly dense. It is retaining up to 14 stops of dynamic range, actively saving all the raw data in the darkest blacks and the brightest whites.
Here's where it gets really interesting. I always like to use a physical packing analogy for this.
Oh, let's hear it.
Shooting in standard color is like packing a suitcase for a trip, but just haphazardly throwing all your bulky sweaters in. The suitcase looks full immediately, it looks great, but you really can't fit much in there. If you want to add something else later, you can't.
Yeah.
Shooting in GPlog 2 is like putting all your clothes into one of those vacuum sealable bags and sucking all the air out. It shrinks everything down. It looks totally flat, wrinkled, and ugly in the bag, but you are actually holding 3 times as much data in the exact same amount of space. You can unpack it later.
That's a great way to think about it.
But this brings up a crucial technical requirement.
Yeah.
If you were going to pack that much data in, you have to use 10-bit color, right?
Absolutely. 10-bit color depth is mandatory if you are shooting in a log profile. Standard video, like what you see on most old TVs or standard YouTube videos, is 8-bit color. An 8-bit file can only record and differentiate about 16 million specific shades of color.
16 million sounds like a lot, honestly.
Now, 16 million sounds like an enormous number, but it really isn't. When you film a wide, expansive, clear blue sky, the camera has to render a smooth gradient from light blue near the horizon to deep blue straight up. An 8-bit file simply runs out of shades of blue to make that transition smooth. What happens is the gradient breaks and you end up seeing these ugly, blocky, harsh rings of color in the sky. That's called color banding.
It looks like a poorly compressed JPEG from the early internet.
Exactly. It shatters the illusion of high quality. A 10-bit color file, on the other hand, can mathematically record over 1 billion distinct shades of color. It has so much color data that it ensures perfectly smooth, flawless gradients in the sky and on the asphalt, no matter how hard you stretch or manipulate the flat log footage later in your editing software.
And it isn't just about preserving color depth, it's about preserving color temperature. The deep dive notes stress the absolute importance of locking your white balance manually, say, to 5500 Kelvin for bright daylight.
Wow, you have to.
Because if you leave white balance on auto while riding a motorcycle, you are creating an absolute nightmare for yourself in post-production.
Yeah, completely.
I mean, the camera's processor is constantly scanning the scene, trying to guess what the color of the ambient light is.
Yeah.
You lean into a sweeping corner under some green trees, the camera sees all that green bouncing around, and it shifts the global tint of the video to magenta to try and compensate.
Right.
5 seconds later, you lean out of the corner, back into the direct sun, and it suddenly shifts the tint to blue. If you try to color correct that footage later, the pavement is literally changing color from gray to purple to blue every 3 seconds. You can't fix it.
No, it's baked in.
Locking it to a specific Kelvin temperature forces the camera to view the world with a fixed perspective, guaranteeing consistency.
Consistency is the absolute bedrock of a professional production. Now, for the truly advanced users, our sources delve into an even deeper layer of hacking. The GoPro Labs firmware.
GoPro, yeah.
This is essentially developer-level access to the camera's core programming matrix. It bypasses the standard menus entirely. By flashing the camera with this specific firmware, you can use an app to generate custom QR codes, point the camera at the code, and instantly input specific hidden command strings.
You are literally feeding code into the lens.
Yes. And one of the most powerful codes for a motovlogger is NR01 equals 1. When you scan this, you are forcing the camera's operating system to completely disable its internal spatial noise reduction algorithms.
Now, wait a minute. Why would you ever want to turn off noise reduction? Nobody likes grainy, noisy video. It looks cheap.
You turn it off because the camera's internal processor is physically small, underpowered, and prone to overheating. It has to perform that noise reduction in real time 60 times a second while you are writing.
That's a lot of math for a tiny chip.
Exactly. It is a very clumsy, blunt force algorithm. When it looks at the fine, gritty, microscopic texture of road asphalt or the sharp edges of gravel on the shoulder, the tiny processor often mistakes that fine physical texture for digital noise.
Oh, so it tries to clean up the road.
So it smudges it out. It aggressively blurs the road to make it look clean. The result is this artificial watercolor-like smearing where the asphalt looks like smooth plastic.
It destroys the physical reality of the environment.
Exactly. By using the NR01 equals 1 command, you tell the camera, stop trying to help me. You capture the raw, computationally untouched, noisy, but highly detailed image. Then you take that file home, put it on a powerful desktop computer with a dedicated graphics card, and you run it through professional noise reduction software, like a plugin called Neat Video.
Okay.
The desktop computer can take its time, sometimes minutes per frame, to perfectly map the temporal noise, mathematically separating the digital static from the actual physical texture of the road. It removes the noise while preserving the grit of the asphalt flawlessly.
The level of control is insane.
Mm-hmm.
But here's where we circle back to the reality of shooting in GP-Log 2. You go through all this trouble, you lock the shutter, you calculate the 180-degree rule, you screw on the ND filter, you shoot in 10-bit log, you turn off the internal noise reduction.
Yeah.
Well, let me avoid the pause. And when you dump that file onto your computer screen, it looks absolutely atrocious. It was washed out, it's gray, it's flat, and it's full of raw sensor noise.
Yep.
To go back to my vacuum-sealed bag analogy, you can't wear the clothes while they're still in the bag. You have to unpack the data in post-production. You have to take that incredibly flat footage into a professional color grading program like DaVinci Resolve, and you have to apply something called a color space transform, or a CST.
Right, the CST.
Let's talk about the math of the CST, because this is where the magic actually happens.
A color space transform is, fundamentally, a complex mathematical translation between two different 3D coordinate systems. Think of a color space as a 3D box, where every possible color is assigned an exact mathematical coordinate.
Okay.
When you shoot in GP-Log 2, the camera captures the color data inside a massive, sprawling 3D box called DaVinci Wide Gamut. This box is huge. It contains coordinates for extreme highlights and deep shadows. The problem is the screen on your smartphone or the YouTube player on your laptop cannot display a box that big.
They use a smaller box.
They operate on a much older, much smaller standard called Rec. 709. Rec. 709 is a tiny, restricted 3D box.
So if you just jam the big box into the small box, you crush the edges and ruin the image.
Exactly. If you just force a DaVinci Wide Gamut file onto a Rec. 709 screen without a translation, the screen doesn't know what to do with the extra coordinates, so it just chops them off. The colors look weird and the image remains flat.
Enter the CST.
Right. The color space transform is a mathematical formula that takes every single pixel coordinate in the massive DaVinci Wide Gamut box and proportionally maps it to a new coordinate inside the smaller Rec. 709 box. It compresses the dynamic range gracefully.
Wow.
When you apply the CST in DaVinci Resolve, it's like watching a magic trick. Instantly, the contrast snaps back into place. The colors become incredibly rich and vibrant. The blacks drop down to true black. But because you originally captured all that data in 10-bit log, the white clouds in the sky maintain perfect, fluffy detail instead of blowing out.
And you can still see the dark mechanical bolts on the engine block in the shadow.
Exactly.
It is a massive amount of technical legwork. But the result is that visceral, commercial-grade cinematic look. But here's the brutal truth of the medium. Cinematic motion blur, perfect color grading, and 14 stops of dynamic range mean absolutely nothing if the audio is just a blown-out, screeching, distorted mess of wind noise.
Oh, 100%.
If a viewer is watching a buttery smooth 4K video, but their ears are being assaulted by digital static and wind tearing over a microphone, the brain rejects the immersion immediately. They will click away in 5 seconds.
Yeah. Optical physics simply do not matter if the acoustic engineering fails.
And capturing clear vocals and the mechanical scream of an engine at 60 miles per hour is arguably the hardest part of motovlogging.
It is the most common point of failure, without a doubt. Sound behaves very aggressively at speed. It is physical pressure hitting a membrane. And before we even get to the microphones, the first mechanical hurdle is simply getting an external microphone connected to the action camera securely without destroying the camera itself.
Right, because the technical guides are incredibly explicit about this. Do not, under any circumstances, rely on a standard USB-C to 3.5 millimeter dongle hanging off the side of your camera on a motorcycle.
They're an absolute liability. Think about the physics of the environment. You have a motorcycle helmet vibrating at intense high frequencies from the engine. Then you have a small, heavy dongle dangling from the camera, and an audio cable catching the aerodynamic drag of a 70-mile-per-hour wind.
Oh man, that's just a recipe for disaster.
That wind drag is violently pulling and vibrating that cable, transferring all that mechanical stress directly into the tiny, fragile, internal USB-C port soldered to the camera's circuit board.
So it's just going to break.
Over time, and usually very quickly, that vibration will literally snap the solder joints inside the camera, permanently ruining the device. The engineered solution to this mechanical problem is the GoPro Media Mod.
The Media Mod. Now, it looks a bit clunky. It's essentially a hard plastic shell that you slide the camera into, right?
It is a structural cage. When you slide the camera in, it docks with a robust, fixed internal USB-C connection that is fully supported by the plastic housing.
Okay, so it takes the strain.
The Media Mod takes the physical strain completely off the camera's delicate internal components. It absorbs the vibrations, and then it outputs a stable, mechanically supported, dedicated 3.5 millimeter microphone port on the outside of the shell.
Okay, so you buy the Media Mod, you snap it on, you take a microphone you bought online, you plug it into that robust 3.5 millimeter port, you hit record, you go for an hour-long ride, you come home.
And it doesn't work.
And there is nothing on the video but rumbling wind noise. The external microphone didn't record a single word. What happened? This brings us to the most frustrating electrical mismatch in the entire motovlogging world. TRS versus TRRS. Let's talk about the electrical ping.
This specific issue trips up more creators than anything else. It all comes down to the physical layout of the metal plug on the end of your microphone cable. If you look closely at the metal jack, you will see thin black insulating rings separating the metal into sections. TRS stands for tip ring sleeve. You will see 2 black rings on the plug. This is the professional analog audio standard used by digital cameras and dedicated audio recorders.
So TRS has 2 rings.
Right. TRS stands for tip ring sleeve. This plug has 3 black rings. This standard was designed specifically for smartphones. The extra ring allows a single plug to carry both a stereo headphone signal out to your ears and a microphone signal back into the phone.
So if you go on Amazon and buy a cheap, highly rated lavalier microphone that says perfect for iPhone, it is almost guaranteed to be a TRS plug with 3 rings.
Exactly. And here is where the electrical failure happens. If you plug a TRS smartphone microphone directly into the GoPro Media Mod, the physical metal contacts inside the port do not align perfectly with the metal sections on the plug. When you turn the GoPro on, the camera's processor sends a tiny electrical ping down the port to identify what kind of device is plugged in. Because the rings don't line up, that electrical ping hits the wrong contact and grounds out.
It grounds out.
The camera's brain assumes the port is either empty or faulty to protect itself from a short circuit. So without giving you any warning on the screen, it quietly defaults back to using its own internal microphones.
Which is catastrophic because once the camera is inside the Media Mod, those internal microphones are buried under plastic and completely exposed to the chaotic wind turbulence wrapping around the helmet.
Precisely. You end up recording an hour of unusable, rumbling, concussive noise. To fix this, you absolutely have to check your gear. You must use a microphone with a TRS plug featuring 2 black rings. Or you must purchase a specialized TRS to TRS adapter cable that mechanically reroutes the internal wires so the GoPro receives the correct electrical ping.
Okay, assuming we have the electrical routing sorted out and the camera recognizes the mic, where do we physically put the microphone? Obviously, it has to go inside the helmet to block the wind.
Yeah, that's crucial.
The sources mention 2 popular options. The Purple Panda, which is an omnidirectional mic that's great for letting a bit of the engine's exhaust note bleed into the vocal track, or the Rode SmartLav Plus Nia, which is a tighter condenser mic that really isolates the human voice. But what if you aren't just talking to yourself?
Oh, group riding.
Right. What if you're riding in a group of 4 people and you want to capture the live banter between you and your buddies? You can't run a wire to their helmets.
That is a completely different acoustic challenge, and that is where sophisticated helmet intercom systems like the mesh-networked Sena 50S or the Cardo PackTalk come into play. To capture that group audio on your video, there are 2 primary workflows. The first is the post-production sync method.
Ah, the classic clapperboard method.
Exactly. Modern high-end intercoms, like the Sena 50S, have the ability to record the entire multi-rider mesh network conversation internally, saving it as a standalone high-definition Bluetooth audio file directly to your smartphone or the intercom itself.
So you just record separately?
You just hit record on the Sena, hit record on the GoPro, and ride. You talk normally. When you get home, you have two separate files. A video file with terrible wind noise, and a crystal clear audio file of your conversation.
And then you have to put them together.
You bring both into your editing software, and you have to manually align them. You do this by clapping your hands loudly in front of the camera lens right before you start writing. In the editing timeline, you look for the exact frame where your hands physically touch, and you drag the audio file left or right until the massive spike in the audio waveform, the sound of the clap, lines up perfectly with the visual impact.
It is a bulletproof, reliable method, but it adds a tedious layer of work to every single video. I always forget to clap, and then I spend 20 minutes trying to read my own lips in the reflection of my mirrors to sync the audio.
Yeah, it happens all the time.
What is the second method that bypasses this?
The second method is the direct attenuation cable method, and it requires understanding signal strength. The goal is to run a physical cable directly from the headphone output of your helmet intercom into the GoPro Media Mod, so the camera records the group chat directly onto the video file in real time, no syncing required.
Sound perfect.
But there is a massive electrical hazard here. You cannot just use a standard, cheap auxiliary cable you bought at a gas station.
Why not? A cable is a cable.
Not when it comes to signal voltage. The audio signal coming out of an intercom is heavily amplified. It is designed to physically push the magnets inside the speakers clamped against your ears so you can hear your friends over a roaring engine. That is called a hot, line level, or headphone level signal.
Okay, a hot signal.
The GoPro Media Mod, however, is expecting a very quiet, delicate mic-level signal from an unpowered lavalier microphone. If you take that heavily amplified hot intercom signal and slam it directly into the GoPro's sensitive mic input, the camera's audio preamps instantly overload. The audio violently clips and distorts.
It sounds like yelling into a blown-out, crackling drive-through speaker at a fast food restaurant. It's horrible.
Precisely. To solve this, you must use a specialized attenuation cable. This cable has tiny electrical resistors physically soldered into the wire itself. These resistors act like a dam, aggressively patting the hot signal down, reducing its voltage by 25 to 35 decibels before it ever reaches the camera.
That makes sense.
This reduces the roaring intercom signal into a quiet, manageable mic-level signal. The GoPro receives it perfectly, records it cleanly, and your group banter is permanently synced to the video.
Now, let's talk about the camera's internal computational audio processing. Because if you dive deep back into the ProTune menu, past the log video settings, there are these raw audio settings that give you immense control over how the camera's computer interferes with the sound.
The raw audio settings determine the level of artificial intelligence applied to your soundscape. If you set the raw audio to low, you are telling the camera to do absolutely zero processing.
Nothing at all.
It disables all wind filtering, disables all mixing, and outputs 3 distinct, raw, uncompressed audio tracks directly from its 3 internal microphones. It is an incredibly quiet, flat file.
So what do you do with it?
You have to take those 3 tracks into post-production, manually boost the gain, and manually pan and mix them. It requires a lot of work, and it's strictly meant for professional sound designers who want total control over the spatial audio mix.
Okay, what about medium?
Medium is arguably the holy grail for capturing raw motorcycle exhaust notes. When you select medium, the camera applies spatial stereo mixing, and it applies a baseline wind filter to cut the low-end rumble. But, crucially, it leaves automatic gain control, or AGC, turned off.
Let's focus on AGC, because leaving that on is how people ruin the sound of their exhaust. Why is automatic gain control so destructive to an engine node?
Think of automatic gain control as an invisible, highly anxious sound engineer living inside your camera who is terrified of loud noises.
Okay, I like that image.
When you are just cruising at a steady RPM, the sound engineer turns the microphone volume up so you can hear the engine purr. But the second you crack the throttle wide open and the exhaust screams, the invisible sound engineer panics. He grabs the volume fader and violently yanks it down to prevent the loud noise from clipping.
Right, so the sound drops.
The exhaust roar gets instantly muffled. Then, when you let off the throttle and shift gears, the engine gets quiet again. The sound engineer realizes it's too quiet, so he rapidly pushes the volume fader all the way back up.
But because the engine is quiet, the microphone just picks up the background hiss of the wind and amplifies it. You get this incredibly unnatural breathing pumping effect where the audio swells and collapses wildly.
Exactly. By setting the camera to medium and disabling the AGC, you remove the panicked sound engineer. The microphone sensitivity is locked. When the exhaust screams, it actually sounds louder on the video, swelling and falling naturally, exactly as the human ear experiences it in real life.
And finally, there's the high setting, which applies everything spatial mixing, aggressive wind filtering, and full automatic gain control. It compresses the dynamic range of the audio entirely. It's best for quick turnaround vlogs where you don't care about the cinematic exhaust note. You just want to ensure your voice is consistently loud and audible without having to touch an audio slider in the editor.
Right, but if we connect this computational processing to the bigger picture of the writing experience, you have to be extremely careful with the camera's general wind reduction setting if you aren't using an external microphone inside your helmet.
Oh, this is important.
If you leave the camera's built-in wind filter on auto, the processor is constantly monitoring the ambient wind pressure. When you are riding slowly through a neighborhood, there's no wind, so the camera records in lush, wide, immersive stereo sound. But the moment you accelerate onto a highway and the wind pressure hits the physical microphones, the processor panics.
So it changes something.
To save the audio from distorting, it aggressively switches the recording from stereo to mono, instantly shutting off whichever microphone is facing the wind.
Which is incredibly jarring for a viewer. If you are watching a video with headphones on, 1 second the sound of the motorcycle is wrapping all around your head in an immersive 3D space. The next second you hit 60 miles an hour, the camera switches to mono, and the entire soundscape collapses into a thin, compressed, flat line right in the dead center of your forehead.
Yeah, it feels like your ears just popped.
It is completely disorienting.
It shatters the immersion instantly. This is why mastering your external audio routing and understanding how to bypass the camera's internal AI is just as important as setting your shutter speed.
Okay, so we have engineered the perfect visual exposure with ND filters and log profiles, and we have broadcast quality audio securely routed past the TRS mismatch. We have the perfect technical pod. Now, where do we actually attach this rig to the rider? This isn't just about getting a cool angle for YouTube. The mounting location dictates aerodynamics, point of view aesthetics, and most importantly, the biomechanical survival of the rider's brain in the event of a catastrophic crash.
Mounting is the most critical physical decision a motovlogger makes, and when you review the aerodynamic data and the safety kinematics, the sources point definitively to one optimal location: the chin mount.
Mounting the camera directly on the front and center chin bar of a full-face helmet. Why is that the undisputed king of mounting points?
We can look at it from two perspectives: aesthetics and physics.
Let's start with aesthetics.
From an aesthetic standpoint, the chin bar places the camera lens as physically close to the rider's actual eye line as possible without blocking their vision. When a viewer watches chin-mounted footage, they see the handlebars, the dashboard, and the vanishing point of the road in a highly realistic first-person perspective. It makes the viewer feel like they are piloting the bike.
Okay, and physics.
Aerodynamically, the chin bar is a crucial neutral zone. The shell of a premium motorcycle helmet is wind tunnel tested to pierce and split the air exactly at the front chin vent. By placing the camera right at that splitting point, tucked tightly against the shell, you keep the device within the aerodynamic boundary layer of the helmet. It minimizes the drag coefficient. Furthermore, the human neck acts as a highly evolved, biological 3-axis gimbal.
Right. Our bodies naturally, subconsciously want to keep our eyes level with the horizon. So as the motorcycle bounces over bumps and leans into corners, our neck muscles are constantly making micro adjustments, absorbing those high-frequency vibrations from the road. The neck stabilizes the head, which stabilizes the camera, making the resulting footage incredibly smooth without the camera's digital stabilization having to work as hard and crop the image.
Exactly. Contrast that biological synergy with the alternatives. Let's look at the top mount, sticking the camera straight on top of your helmet.
To be blunt, it looks completely ridiculous. You look like a Teletubby riding a sport bike.
It isn't a great look, no. But more importantly, the physics are terrible. By placing the camera on top of the helmet, you are thrusting a square block directly into the high-velocity, undisturbed airflow streaming over the rider.
Like a sail.
At 80 miles per hour, that air hits the camera and creates a massive aerodynamic lever. The wind drag constantly tries to pull the rider's head backward. Over a 2-hour ride, fighting that lever arm causes severe neck fatigue and muscle strain.
And aesthetically,
Visually, it makes the footage look disconnected because the camera is so high you lose sight of the motorcycle's controls. It just looks like a detached drone hovering awkwardly above a bike.
And the side mount sticking it on the left or right ear of the helmet is even worse, isn't it?
Drastically worse. A side mount creates profound asymmetrical drag. The wind is violently pulling on the right side of your head, but not the left. Your neck muscles have to constantly fire asymmetrically just to keep your head looking straight down the road.
That sounds exhausting.
It is exhausting and distracting. And from a framing perspective, it's awful. Half the video frame is entirely blocked by the side of your own helmet.
But the real discussion here isn't just about neck comfort or getting a pretty shot. It is about trauma. The deep dive documentation goes extensively into the Department of Transportation's FMVSS 218 safety standards for helmets.
Yes, the Federal Motor Vehicle Safety Standard 218 is the legal and mechanical baseline for helmet safety in the United States. And this regulation contains a very specific, explicit rule. A certified motorcycle helmet cannot have any rigid external projections that exceed 5 millimeters from the outer spherical shell.
5 millimeters. A GoPro in a media mod is vastly larger than 5 millimeters. So, technically speaking, the moment you strap an action camera to your helmet, you are actively compromising its DOT compliance and its engineered safety profile.
Both legally and mechanically, yes. You are violating the design parameters of the helmet. And the biomechanical science behind why that strict 5 millimeter rule exists is incredibly sobering. It comes down to the mechanics of traumatic brain injury, or TBI.
Okay, explain that.
When people think of a motorcycle crash, they usually think of linear deceleration, your head moving forward, hitting a concrete wall, and stopping instantly. Helmets are great at absorbing linear impacts with EPS foam, but brain trauma is heavily driven by a different force, rotational kinetic energy.
The physics equation highlighted in the biomechanical safety study is EK equals 12 I omega squared. Let's translate that math for the listener because it explains exactly why a camera can be lethal.
Let's break the variables down. EK represents the total rotational kinetic energy tearing at your brain. I is the moment of inertia, basically the mass and shape of your head and helmet. And omega is the angular velocity, or how fast your head is whipping sideways. Notice that the angular velocity is squared.
Omega squared.
That is the terrifying part. It means that as your head spins faster, the destructive energy doesn't just double, it increases exponentially. Now imagine you crash. You fall off the bike and you slide across the asphalt. You have a high linear velocity. You are moving very fast in a straight line.
Right.
A smooth, round helmet is designed to slide across the pavement, glancing off curbs and allowing that kinetic energy to bleed off slowly through friction without twisting your neck.
But if you have a rigid aluminum-reinforced camera mount sticking 3 inches out of the chin bar,
that rigid mount becomes a mechanical lever arm. If that protruding camera snags on a curb, a crack in the road, a rock, or even just high-friction asphalt while you are sliding, it acts as an immediate pivot point.
so it stops the slide.
It instantly catches and stops the helmet from sliding, aggressively converting all of your forward linear velocity into violent rotational acceleration. It snaps your head violently to the side, generating massive angular velocity.
And because of the omega squared in the equation, that translates to an exponential spike in rotational energy applied to the skull. And here's the gruesome part about the brain. It isn't a solid, rigid block of muscle. It has a very high water content and incredibly low shear stiffness. It's almost the consistency of thick gelatin.
Exactly. When the skull rotates violently due to that snagged camera, the skull moves, but inertia dictates that the gelatinous brain inside wants to stay exactly where it was. The outer layers of the brain are dragged by the skull while the inner layers lag behind.
Wow.
The brain tissue physically twists, stretches, and shears against itself. That internal shear strain is what physically tears axons, the long, delicate nerve fibers connecting brain cells, and ruptures blood vessels. It is called diffuse axonal injury, and it is the primary mechanism of severe, permanent, traumatic brain injuries and comas.
So if having a rigid block on your helmet can literally tear your brain apart by snagging the pavement, how do we mitigate this risk if we still want to film our rides? The research points emphatically to engineered breakaway mounts.
Breakaway mounts are absolutely non-negotiable for anyone who values their cognitive function. Brands like Chin Mounts or Promoto do not just sell universal blocks of plastic. They use 3D scan data to print brackets tailored to the exact specific curvature of individual helmet models, like a Shui RF1400 or an RA Corsair X.
So it fits perfectly.
But the crucial engineering lies in their failure points. These mounts are intentionally designed with specific structural weaknesses. They use thin plastic shear pins in the hinges, or they use a calibrated low-shear VHB adhesive to attach to the helmet.
I always compare this to modern Formula One car design. If you watch a Formula One car hit a wall at 150 miles an hour, the car absolutely explodes. 1,000 pieces of carbon fiber shatter into the air.
Right.
To a casual observer, it looks catastrophic and terrifying. But it is meticulously engineered to do exactly that. By shattering and exploding outward, the car is violently shedding kinetic energy away from the driver's rigid carbon fiber survival cell. The camera mount on a helmet has to perform the exact same function.
That is a perfect analogy. The mount must be sacrificial. If the rider crashes and the camera impacts the asphalt, the force applied to the mount spikes. If that force exceeds a specific calibrated threshold, a threshold carefully calculated to be far below the amount of torque required to snap the rider's neck or rotate the skull dangerously, the 3D printed bracket is designed to shatter instantly.
So it just breaks off.
The plastic pins snap, or the adhesive gives way, instantly ejecting the camera and the mount away from the rider. The lever arm is removed in milliseconds, allowing the smooth, spherical shell of the helmet to hit the ground, slide safely, and do its job.
And while we are on the topic of sensory protection and the brain, there is another massive biomechanical risk we have to address. We spend all this money, time, and engineering to perfectly capture the beautiful audio of the motorcycle exhaust for the viewer. But the rider has to protect their own ears from the reality of the environment.
The acoustic environment inside a motorcycle helmet at highway speeds is incredibly damaging. Even in the most premium, aerodynamically quiet helmets, the physical turbulence of the wind tearing over the shell regularly generates internal noise levels exceeding 100 to 105 decibels.
That's loud.
Prolonged exposure to that sheer volume of acoustic pressure rapidly destroys the tiny hair cells in the cochlea, causing permanent, irreversible sensorineural hearing loss and chronic tinnitus.
And one of the sources we reviewed included a terrifying anecdote from an older rider who spent decades riding without ear protection. He shared his medical audiogram, and it didn't just show general deafness. He has a specific deep slot missing from his hearing profile.
Yeah, that was wild.
He is completely deaf to the exact specific frequencies that match highway wind noise. But the real kicker, the part that really scared me, is that human speech operates across a wide band of frequencies. Because he lost his hearing in that specific wind noise slot, he also permanently lost the cognitive ability to understand human speech when people talk using those specific frequencies.
It's devastating.
He didn't just turn the volume down on his hearing. His brain literally lost the hardware required to decode the sound of consonants.
It's a tragic and entirely preventable loss, which is why utilizing high-grade earplugs is just as vital as strapping on the helmet itself. The data strongly recommends industrial-grade foam plugs like the 3M EAR Soft FX, which, when inserted correctly deep into the ear canal, offer a massive 39 decibel reduction in noise.
Okay, or custom ones, right?
Alternatively, riders can invest in custom molded silicone plugs, like those manufactured by Ultimate Ears, which are poured to match the exact shape of the rider's ear canal. These custom plugs use specific acoustic filters to block the damaging low-frequency roar of the wind while intentionally allowing the higher frequencies of sirens, car horns, and your intercom speakers to pass through clearly. You protect your brain without isolating yourself from your environment.
Okay. We have engineered the perfect technical pad. We have a 10-bit log profile camera shooting through ND filters with a locked 180-degree shutter. We have impedance-matched audio running through attenuation cables to bypass the camera's AGC. And we have securely mounted all of this to the aerodynamic neutral zone of the helmet using a sacrificial shear pin breakaway mount.
We have built the ultimate setup.
We have. Now, what happens when we take this perfect cinematic rig and strap it to a rider piloting one of the most ferocious, uncompromising superbikes on the planet?
We meet our test subject, the 2025 Ducati Street Fighter V4S.
Just saying the name invokes a certain level of intimidation. This is what the industry calls a naked bike. which means the engineers stripped away all the aerodynamic plastic fairings, leaving the rider completely exposed to the wind blasts.
Yeah, no protection.
It features a 16-liter aluminum tank, massive Brembo high-pure progressive braking calipers, and a 1103cc Desmosedici Stradale V4 engine that produces 214 horsepower right out of the factory crate.
It is an absolute masterpiece of Italian mechanical engineering, but as the detailed tuning data from our sources reveals, the factory version of this bike is actually heavily, almost criminally compromised.
It has 214 horsepower. How can a machine that fast be compromised?
It is compromised by bureaucracy. To legally sell this motorcycle globally, Ducati must ensure the bike passes incredibly strict Euro 5+ and US EPA emissions and noise regulations.
Emissions.
To pass those laboratory tests, the factory ECU, the computer that runs the engine, aggressively chokes the performance. The software restricts how far the electronic throttle blades are allowed to open in the lower gears, regardless of how hard the rider twists the grip. The fuel mapping runs dangerously lean to reduce emissions, and the exhaust flow is physically strangled by massive, heavy, heat-retaining catalytic converters.
Enter the engineers at BT Moto and their Stage 1 Plus performance calibration. This is where the real deep dive engineering comes in. They don't just plug a laptop in and tweak a few generic numbers. They completely reverse engineer the Bosch ECU architecture.
The BT Moto software flash completely transforms the mechanical behavior and the thermodynamics of the motorcycle. By overriding the factory emissions restrictions, optimizing the ignition timing, and richening the air-fuel ratio, they yield a massive 30-wheel horsepower gain right at redline.
Wow.
They push the bike to a verified 197 horsepower measured directly at the rear tire. But the horsepower number is just a headline. The true engineering value of the tune is in the drivability.
Right, because if you've ever ridden a highly strung modern sport bike, you know the absolute terror of the dreaded jerk. You are aggressively entering a corner, you roll off the throttle to shift the weight to the front tire, and the bike violently pitches forward. Then, at the apex, you crack the throttle back open a millimeter, and the power snaps back on so violently it snaps your neck back and upsets the suspension.
That jerkiness is caused by the factory deceleration fuel cutoff mapping. To save microscopic amounts of fuel and reduce emissions on closed throttle deceleration, the factory ECU completely shuts off the fuel injectors the exact millisecond you close the grip.
Well, that makes sense.
It causes a harsh, abrupt engine braking effect. The BT Moto software fixes this by actively maintaining a tiny, continuous pulse of fuel into the cylinders even during deceleration. This keeps the engine internally loaded, completely eliminating the jerk and making the transition back onto the throttle buttery smooth, which is critical for mid-corner stability.
They also tackled the cylinder deactivation. To keep the bike from literally roasting the rider's legs at a stoplight, the Ducati is programmed to shut off the rear two cylinders when idling. It essentially becomes a twin-cylinder bike.
Right.
But when you start moving, the computer has to reignite those two cylinders, and the transition back to a full V4 can be clunky and hesitant. The BT Moto Tune smooths out that reactivation threshold. And speaking of roasting the rider, the thermal management data on this bike is wild.
The thermodynamics of a V4 engine packaged that tightly are extreme. The factory ECU, again for emissions efficiency, allows the engine coolant to reach a scorching 220 degrees Fahrenheit before it even commands the cooling fans to turn on.
220 degrees.
If you are stuck in gridlock traffic, that radiant heat bakes the rider's legs, and more importantly, it causes the engine oil viscosity to begin breaking down. BT Moto drops that fan activation threshold significantly, commanding the fans to kick on at 190 degrees Fahrenheit. It protects the engine's internal components and makes the bike actually livable in a dense, slow-moving city environment.
And they even rewrite the code for the exhaust butterfly valves, forcing them open earlier to make the stock exhaust roar at lower RPMs. But let's be honest, if you are going this far into the engineering of the bike, you don't keep the heavy, restricted stock exhaust. Our technical build sheet details the addition of the Terminioni underseat slip-on exhaust.
Part number D24209400ITC. It is genuinely a work of art, crafted entirely in lightweight titanium and carbon fiber.
It fundamentally changes the architecture of the bike. It completely deletes the heavy, heat-soaking catalytic converters located under the engine, and it physically relocates the exhaust exit routing directly up and under the rider's tail section, mimicking the aggressive style of a MotoGP race bike.
Which saves a lot of weight.
That physical change sheds 6 kilograms over 13 pounds of dead weight from the chassis. The improved airflow frees up another 12 horsepower, pushing the total system output to an absolutely staggering 226 crank horsepower.
And the acoustic profile it generates is violent. If you run the system without the sound-deadening dB killers installed, the exhaust registers a deafening 105 decibels at just 5,500 RPM, which isn't even halfway to redline.
Unbelievable.
This circles right back to our previous discussion. This is exactly why you need those 39 decibel reduction earplugs. The sound pressure level of that exhaust note reflecting off the pavement is physically concussive to the human ear.
So you have a stripped-down naked bike putting 226 horsepower down to the asphalt with no aerodynamic fairings to keep the front wheel on the ground. What tires are possibly translating that immense rotational force into forward momentum without instantly spinning up into a cloud of smoke?
For a machine with this level of extreme potency, tire selection is hypercritical. It's the only thing keeping you out of the ditch. The data we are referencing is the massive 2025 Sport and Hypersport motorcycle tire test conducted by PS Magazine. Crucially, they conducted this test on a closed track in ambient temperatures of 14 to 18 degrees Celsius, which is a brisk, cool environment, not a scorching hot summer day.
And the data from that test was surprisingly nuanced. It completely upends conventional wisdom about just buying the most expensive track tire. We are looking at a battle between two absolute titans of the rubber industry, the Dunlop SportSmart MK4 and the Pirelli Supercorsa SPV4.
The Pirelli Supercorsa SPV4 is the quintessential no-compromises track day hypersport tire. It is essentially a racing slick with just enough grooves cut into it to be street legal. It relies heavily on carbon black in its compound.
Okay.
When the track is completely dry and the rider pushes hard enough to generate massive internal heat inside the carcass, the Pirelli dominated. It posted a blisteringly fast 79.82-second lap time. It provides maximum edge grip at extreme lean angles and feeds incredible tactile feedback through the front forks. If you are taking the Street Fighter V4S to a dry, hot racetrack, the Pirelli is the undisputed weapon of choice.
But, we don't live in a perfectly controlled world where it's always dry, the track is rubbered in, and the asphalt is baking in the sun. Motovloggers ride in the real world.
Exactly. And that real-world unpredictability is exactly why the Dunlop SportSmart MK4 actually won the overall test, despite not being a pure track tire. The Dunlop is categorized as a high-performance street sport tire. Instead of relying purely on thermal buildup for grip, the Dunlop compound features of a very high concentration of silica.
Silica, what does that do?
Silica is a chemical compound that drastically lowers the glass transition temperature of the rubber. This means the tire remains soft, pliable, and sticky almost instantly upon rolling, even on cold, brisk mornings. When PS Magazine ran the wet handling course, simulating rain and damp conditions, the Dunlop was absolutely untouchable.
Really?
It laid down a 72.64-second lap time, beating the aggressive Pirelli and every other hypersport tire by a massive, undeniable margin.
So think about what that means for a rider out in the canyons. If you are a motovlogger carving through mountain roads early in the morning, and you sweep through a sunny corner only to hit a freezing damp patch of asphalt hidden in the deep shade of a mountain, the high silica Dunlop gives you a massive, life-saving margin of safety that the temperature-dependent Pirelli simply cannot offer. It's not just about theoretical peak dry grip. It's about chemically matching the rubber compound to the chaotic reality of the environment.
Precisely. It is engineering for survival over absolute peak performance.
Which brings me to a quote from former Grand Prix racing legend Neil McKenzie that was highlighted in the sources, and it really stuck with me. When discussing riding motorcycles of this caliber on public roads, he says you have to adopt a specific psychological framework. You have to pretend it's a video game. Every blind junction, every distracted driver in an SUV, every patch of gravel in a corner is an active enemy actively programmed to take you out.
It is the ultimate defensive mindset.
Which begs the question, to wrap all of this up, what does this all mean for the creator? Can you actually daily drive a 226 horsepower Ducati Superbike while simultaneously trying to operate a complex camera rig and narrate an entertaining video?
The consensus from the data and from anyone who has attempted it is, well, technically yes, but practically, it demands an immense, almost exhausting level of mental discipline. To put this in perspective, the article discussing beginner motorcycles notes that a 650cc twin-cylinder bike making maybe 70 horsepower is considered beginner plus territory.
So jumping on an 1100cc V4 producing over 3 times that power, weighing under 450 pounds, is essentially strapping yourself to an unguided missile if you aren't paying total attention.
Exactly. The Street Fighter V4S is not a commuter vehicle. It is an exotic, highly strung performance machine. Riding it requires absolute respect for the throttle, top-tier protective gear, and constant draining mental focus. If you try to commute on this bike in gridlock traffic, the heavy clutch pull, the aggressive pitched forward seating position, and the sheer radiant heat of that V4 engine will make you absolutely miserable. It is a Sunday weapon designed strictly for sweeping open roads and dedicated track days.
And if you are out on that Sunday ride trying to operate a complex GP Log 2 camera rig, monitor your attenuation cable audio levels, mentally script and narrate a compelling story, and keep 226 horsepower from launching you into the trees, you are completely maxing out the human brain's processing power. You have to have the physical act of riding the motorcycle dialed in so perfectly, so completely subconscious, that it leaves cognitive room for the video production part.
Which is exactly why automating the camera technology is so vital. This is why we spent so much time discussing locking the protein limits, setting the 180-degree shutter, using ND filters, and configuring the raw audio profiles to bypass the AGC. You do all of the complex engineering and math in the safety of your garage, setting the system to run autonomously so that when you are on the road, you don't have to touch a single button. You can dedicate 100% of your cognitive load to surviving the ride and delivering the narrative.
Okay, let's bring this all together. We started with the chaotic, disappointing reality of a shaky, wind-blasted, blown-out video, and over the course of this deep dive, we have meticulously built a system to conquer it. Capturing the perfect motovlog is an incredibly delicate, interlocking puzzle of scientific disciplines. You have to master the optical physics of 10-bit logarithmic sensors, quad-bare pixel binning, and 180-degree shutter speeds. You have to navigate the electrical engineering of impedance-matched microphones, TRRS pings, and attenuation cables. You must adhere to the biomechanical safety of aerodynamic, shear pin chin mounts to prevent rotational brain trauma. And you have to balance all of that delicate technology on top of the raw, terrifying mechanical power of a tuned 226 horsepower superbike rolling on temperature-specific high silica rubber.
It is a remarkable convergence of different scientific and engineering disciplines, all harnessed just to produce a 10-minute cinematic video for YouTube. But reviewing all of this data together leads to a rather provocative thought about the future of this entire process and where the industry is inevitably heading.
Let's hear it. Where does this go next?
We talked extensively about the Department of Transportation's FMVSS 218 regulation, the strict, uncompromising 5mm limit for external projections on a helmet shell. We know definitively from the biomechanical data that strapping a rigid action camera to your face creates a dangerous lever arm that drastically increases rotational brain trauma in a crash. We are currently using engineered breakaway mounts as a clever Band-Aid solution.
Right, but what's the real solution?
But look at the relentless pace of technological miniaturization. We already have 1-inch sensors and tiny action cameras. Given the absolute necessity of aerodynamic safety and the legal liabilities involved, how long will it be before regulatory bodies simply stop allowing external mounts altogether? How long until premium helmet manufacturers brands like Shui or Arai simply start embedding 1-inch optical sensors, 32-bit float internal microphone arrays with AI wind cancellation, and heads-up display telemetry directly into the carbon fiber layers of the helmet shells themselves right at the factory?
Wow. Creating a perfectly smooth, aerodynamically flawless, DOT-compliant, cinema-grade smart helmet right out of the box, making the entire concept of an external bolt-on action camera completely obsolete. That is a wild and highly probable thought to leave on. Maybe the perfect motovlogging camera of the future isn't a camera at all. It's just your helmet. We want to thank you for joining us on this deep dive into the bleeding edge of motorcycle cinematography, acoustic engineering, and hyper-naked performance. Take these ProTune settings, test these audio routes in your own garage, and most importantly, keep learning. Keep your head on a swivel and ride safely out there. Remember that image we started with? The blurring asphalt, the G-forces, the perfect symphony of speed. With the right engineering, you don't just have to remember it. You can finally show it to the world exactly how it felt.